Okay, let's get started. This is the fourth class, right? And I will encourage you, for those in the live classroom, to just look around. Already, people are starting to drop off out of attending the live class. It's your decision, but generally speaking, you do way better if it's possible for you to attend the live class, pay attention, and do whatever. So I'm just pointing out something to think about. I mean, if you look around, you see the attendance drops. And again, not saying that's a preview of what people's grades are going to be, but you get out of something what you put into it. So just think about how much effort it takes to come to class and the value associated with it. So anyway, I thought I would just share that with you because I think it's an important thing to identify. Only 4 classes in, right? So for what it's worth. Anyway, let's get started. This is finishing up chapter 2, which this will be the kind of the key thing for doing our first lab. And the reason why we have to develop this approach, this what we'll call Y-bus approach, which is kind of the key takeaway from this. We do also cover some 3-phase, which is another important topic, but hopefully most of you all have seen that when you've looked at some AC circuits. But the reason why we have to spend a little bit of time understanding how to build what we call Y-bus is because in a real world power system, you might have millions and millions and millions of nodes that you're needing to calculate voltages for. And if you remember from your circuit analysis days, when you actually went and calculated node voltages, you had to write an equation for every node. And if you have a million nodes, you have to basically write a million equations, right? Or a million equations minus 1. The problem with that is once you start solving for the voltages, you have to actually start substituting in, right? Solve for one variable, for the other variables, substitute that in, and then keep substituting that in until you're finally left with one equation with one variable in it, and you solve and you back calculate that way. That's not practical for a million equations, right? You just can't do it that way. So what they've developed is the approach for Y-bus, which is just a very generic way to solve problems where as long as your system is set up correctly, then you don't actually have to do a lot of additional work, and you definitely don't have to solve simultaneous equations. By the way, for those of you who like doing math, how do you, what's the most efficient and effective way to solve a bunch of linear simultaneous equations? Anybody know? Yeah, use matrices, right? Put them in matrices, and then you have one equation, if you will. Now, you might have multiple numbers in that equation, but you have one equation that you can go and you can solve for whatever you need to. And so really what we're going to be doing is building Y-bus, which is another way to say, and a matrix of all the system admittances. And we'll explain why admittances is the right way to go in a little bit. So that's all Y-bus is building a system matrix that contains all the admittances as long as they're correctly configured for that system. And once I build that, I'll be able to tell you gobs and gobs of information about the system. And so one of the very first things that when you do a systems analysis is you start off with what's called a one-line diagram, which has some basic connection and rating information. And you'll take that system, because it's, again, it's lines, it's generators, it's transformers, and you're going to convert those all to impedances and then start analyzing the system. Well, the fastest way to analyze a system is to convert that to Y-bus. So then once you have it as a number, then you can pull out whatever calculations you need. And if you use any power systems analysis tools like Easy Power, Aspen, Power Tools for Windows, there's all kinds of different ones. That's what's happening under the hood. They're building a Y-bus under the hood. So you have a graphical interface to show, this is what the lines interconnect to. But underneath the hood, they're actually just building Y-bus. And so we'll talk about some of that stuff here in a minute. So the key thing about building Y-bus is everything has to be in parallel, or you have to make it in parallel to be able to do this work. All right. So if you have a system that looks like this, then all those systems are in parallel, all those individual loads are in parallel with each other. If you have something that is added on and looks like that, well, those two resistors are not in parallel with each other. They are in series with each other. So you have to convert that to an equivalent resistor and then replace the original 2 resistors by the equivalent resistor. And that's why we want to talk about lumping them together as long as they're in the correct form, which means they're all in parallel. Loads, you normally talk about loads as what we call a constant power load, which means the power that is being drawn by that load is the same regardless of the applied voltage. Okay. And that's a fairly easy assumption to make because for the most part, if we're trying to bake bread or something like that, and the oven temperature is too low, then what ends up happening is you'll either adjust the temperature up, right, to put more power into the system, or somebody will have an automatic control system that'll do it. Like on your stove or your refrigerator, they have a temperature monitoring thing, and that'll just keep cycling things on and off until it gets to the desired temperature. So the load is essentially the same. If you have a fixed resistor or fixed inductor or fixed capacitor, those are called constant impedance loads. Okay. So we have two types. We have constant impedance and we have constant power. We're going to focus on keeping the loads constant power. And while we treat them as constant power, we do not include them in our admittance matrix because we don't know what they are, right? To determine what the actual admittance of a load is, if the power is constant, but the voltage is changing, Q equals V squared over X. Well, the V is always changing, so that X value is always going up or down. What I mean by that is, if I have this equation, whoops, I'm not sure why that just did that. Sorry about that. If I have this equation over here, and remember, we talked about magnitude of V, okay? So our X value, so Q is fixed, it's not changing, but V going up or down, which means X is going up or down. So you don't have a way of modeling that as a fixed impedance if you allow that power to be constant. So the way that you do that is we don't include any loads in our admittance matrix. So we're going to do that for power. We're going to lump as many loads in as possible or as necessary, I guess is a better way to describe it, because we don't want to look at 17 million loads all at once. We want to try to lump them together so that maybe we have 1,000 or 2,000 loads. It'll make the analysis a lot more practical. Transmission lines, a real world transmission line, and we'll look at this in a little while. Looks like this. So that is the most accurate representation of a transmission line. What we're going to do is replace that with just one impedance. So we'll either figure out how to include the capacitances in the network, the system elsewhere, or we'll just neglect them completely. And we're going to do nodal analysis. And if you all remember from nodal analysis, right, we have a common node or common nodes, and we're assigning or solving for KCL. The sum of the currents into the node equals the sum of the currents out of the node. And so if we assume that current like that, and this is our V1 node, we have IN equals V1 divided by R1 plus V1, sorry, divided by R2, right? And if we do a little bit of work, we see that IN is going to be equal to VN, 1 over R1 plus 1 over R2. That's equal to VN, and we product, well, we have to do a common denominator before we say product. So that's R1, R2, R2 plus R1. So when I'm all said and, why is this doing this? I have no idea why it's stopping. So when we're all said and done, no idea what's, like it keeps going back to this page. VN divided by IN, which is the effective impedance seen by the source, we'll call that R equivalent, right? So what is that equal to? Well, if we look at this equation here with that, then we see that it's R1, R2 over R1 plus R2. So if you remember way back in circuit analysis, the way that you put resistors in parallel with each other is you take the product over the sum, or you do 1 over R1 plus 1 over R2, and you invert it, right? Remember that from your original circuits days? Which this works perfectly fine. But in this example over here, I have 5 loads. So I would have to do all the number of loads that I have and invert them, right? It gets to be a lot of work. So what I'd rather do is, if things are in parallel, use the concept of a admittance, which is just the inverse of impedance. So if I redo this R1, R2 over here, and now I put them as G1 and G2, so those are called conductances, then G total, which is the total conductance, is G1 plus G2. Well, that's 1 over R1 plus 1 over R2, and 1 over G total is equal to R total, which is 1 over R1 plus 1 over R2 inverted. So we get the exact same result as if we did it, the old-fashioned way, which is 1 over R1 plus R over 1 or 1 over R2 inverted, or we can just add them up. We invert them first and then add them up. And as long as we do our analysis without having to invert things back, then it's a much more efficient way to do things. So pretty much in this semester, you're almost always going to be using admittances when you're doing a fair amount of calculations. You're going to be pulling data out, but you'll be working primarily with admittances or getting it impedances from the admittance data that you put together for your model. So remember from nodal analysis, it's a 3-step process. Find the nodes. You have a reference bus, and then you have however many node voltages that you're trying to solve for. You're going to write KCL equations at each of those nodes, except the reference node. And you're going to write nodal equations. So here's a system, 4-bus system. Actually, 4 bus with a reference, right? So really it would be 5 buses or 5 nodes. And a bus is what we typically call things in electrical utility world. We never call them nodes. They're always called buses. And we can see that we have 3 generators, and they're cranking out power to a common bus. And then that bus may or may not be connected to anything else. Over here, we see that it's not connected to anything else. But in reality, you're probably not just going to connect 3 generators together and do no load to them. That wouldn't make a lot of sense. And so then we're going to tweak that a little bit, because each generator has an internal impedance. Anybody know why generators have an internal impedance? Yes, sir. Say more. The windings, you might be on the right track. It would be the generator, right? So let's call it a machine. Yeah. So they generate things, but why would that give you an impedance or a resistance? It doesn't generate, it has inductance, but it doesn't generate inductance, right? It's configured so it has to look like an inductor. But why would you have a generator that looks like a voltage source in series with some sort of impedance? I don't know. There's an internal impedance. Why is that internal impedance there? Because it's not. That's exactly right. Is there such a thing as an ideal voltage source in the real world? Does everybody know what an ideal voltage source is? Yep. No. You put 12 volts on it, or let's say it's rated for 12 volts, and an ideal voltage source will maintain 12 volts regardless of the load on it, including a dead short circuit, right? So if you put a dead short circuit across a 12-volt source, if it's ideal, it will generate millions and millions, an infinite amount of amps to maintain that voltage. Can that happen? No. So any real world voltage source, the way you represent it is with an ideal source, as shown here, and an internal impedance, which limits the output of the machine. So you're right that it does have an inductance or an internal inductance, but the reason why we actually do that in there is because we have to limit the amount of energy out of the power supply, right? So under short circuit conditions, you're not putting out infinite amount of amps. you're putting out maybe 200,000 amps or 50,000 amps, whatever it works out to be. And that impedance is proportional or equivalent to whatever it needs to be to knock that value down. Okay? So that's the internal generator impedance, and a transformer, whoops, also has an impedance because you have a step-up transformer. Generators, depending on the size, generators, probably most of the generators that you'll come across in the utility world, 4160 would probably be about the lowest voltage you would find. And the biggest voltage you'll ever find is around 25,000 volts. So not a big range, a difference in between the two. There's some reasons for that, but for the most part, that's all what the generators do. So you got to step that voltage up to the transmission level, 345 kV. So you have an internal impedance inside the transformer, and you got to model that before you get to the high side of the transformer and interconnect into the system. And then all those impedances between the buses are just the impedances of the transmission system itself. So I would like to do nodal analysis on this, but I can't, can I? Because the premise of nodal analysis is everything is in parallel, right? These are all in series, aren't they? So the very first thing you do, and this is the most important thing you do, you have to combine all your series resistances or series impedances first. You can't do anything with Y-bus until step one, combine any series impedances, okay? This here is not in series with that directly, right? You've got nodes going off in different directions. So that's not necessarily in series with that bus. So we don't have to worry about that. It's just that when we're going from bus to bus, if you have any impedances between those two buses, those will be in series with each other, most likely, and you've got to combine those first. As we've done here, you'll see that I've combined these. Very first thing I did, step one, I combine those series impedances. Once I combine them, now I'm doing things with admittances, which means all those impedances in my system, I have to invert. So now I've got Y14, Y24, Y34. All those are just found from inverting the individual impedances between bus 1-4, bus 2-4, bus 3-4, on and on and on. And the other thing is, because I'm doing Kirchhoff's current law at the bus, I have to do Norton equivalence at each of those buses, right? How do I solve for the current going into a bus if I have a voltage source in series with an impedance? I have to do a Norton equivalent to be able to do that, right? So I'm going to convert all those voltage sources into current sources using my Norton equivalent. And at that point, I just start writing KCL equations. So for this node right here, or this bus, which is bus 1, all the current going in, IG1, equals the sum of the currents out. And be very careful. You'll notice it's V1 times Y1, not divided by Y1. It's multiplied by Y1 because Y1 is the inverse of impedance. Y1 is 1 over Z1. So when I look at this equation and I write it as an actual resistance, you can see that I get V divided by Z, right? Ohm's law. So remember, or try to remember when you're doing this work, do not divide by an admittance. You should always multiply by an admittance. And then I solve for the current between bus 1 and 4, Y14 times V1 minus V4. Excuse me. Same thing for 2 to 4. Actually, not 2 to 4, because the current the current that goes between bus 2 and 4 is not actually leaving node 1. It's only between 1 and 2. And that's how I get this node equation.
What do you get the V1 and V2?
V1 and V2. This is node V1 or bus V1. This is V2. This is V3, and this is V4. Those are our 4 bus or node voltages. Okay, we assigned those previously, bus 1, 2, 3, 4. So I didn't write bus 1, 2, 3, 4 on here because the figure was getting a little bit busy. And so you can take a look at the other nodal equations. This is not a class in AC circuits. So hopefully I don't need to go over the nodal analysis approach because we really don't need to do nodal analysis other than just explaining where the method comes from. All right, so we're going to write those all together. And again, as one of your classmates mentioned, is let's go ahead and let's put this into a matrix and solve for the matrix. So I have all my knowns, IG1, IG2, IG3. There's no current being injected to bus 4, so that's equal to 0. Is equal to, look at row 1, column 1, which is sometimes called the self-admittance. It's the sum of all the admittances connected to bus 1, right? I have Y1 here, Y12, and Y14. Yes, sir.
You said B1, B2, B3, B4. How about the bus at the bottom, the B5?
This right here?
Yeah.
It is a node, but it's our reference node, right? So everything is referenced to that point. So for the most part, we'll assume that that's 0 volts or at 0 volts. If it's not, you just assume it's 0 volts. And let's say it's at 10 kV, all your voltages will float up 10,000 volts higher. So we can't solve for all the node voltages in the system without having at least one reference bus. That's the reason why we don't touch that one. Oop. So for our self admittance, that's the sum of all touching admittances. And the self admittances are the diagonals. It's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and on and on and on and on until however many buses you have. So those diagonals, how you find them is you sum all the admittances that connect to that bus. Okay. Now, the off diagonal, sometimes called the transfer admittance, is the negative of the actual admittance between buses. So in row 1, column 2, we have the negative of the actual admittance between bus 1 and bus 2. Right? That's important to have the negative. And the negative comes from, well, when you set it up, it's going to come from, let's see, you should have negatives in here. I'm not sure why that's not a negative, but that should be a negative number. So let me correct that. That should be negative, negative, negative. All you have are positives, and the rest are negative numbers. So all the off diagonals, the way that you find those is just take the negative of the actual admittance between the buses you're solving for. So if this is position in Y bus, so we have Y bus 3, 4, it's the negative of the admittance between bus 3 and bus 4. And one thing, if you notice anything about matrices or know anything about matrices, which is there's a concept of a symmetrical matrix. Everybody know what a symmetrical matrix is? If A is symmetrical, then A transpose. Pardon? No, if A is a symmetrical matrix, then the transpose of A equals A. So the off diagonals are the same. And actually the diagonals are the same too. So rows become columns is essentially what that means. So if you know the upper part of your matrix you don't have to do any more work because you know that you have symmetry about there. So you just take the transpose of the matrix and you've got that build. So now, yes, sir. Shouldn't be there. That's a relic. Let me clean it up. I'll put the pluses here too. I don't know why this is acting so weird. So let me delete that. These should all be negatives. And there is no J term here, so that should go away. Thank you. Any day now. So the negatives are there. If there's a J term inside of it, class, I can't attend the meeting, sorry. If there's a J term in it, you just take the negative the J term. So most real world systems are going to look something like this. If you simplify it down, you might have negative J3, positive J2, positive J1, 0. And then this might be minus J7, 5. And this would be J1 and J1. And on and on and on. So most of the time, your negative J numbers are going to live in the diagonal. And then the off diagonal, they'll be positive J's. And that's because when you invert, if it's an impedance that's reactive, when you invert it, it becomes a negative J, right? Because we talked about a 3 ohm reactor or inductor is J3. And then when you invert that, that becomes 1 over J3, which is negative J 1/3. When you take the negative of that, you end up with positive numbers. Okay. So this is our form. This is Ohm's law. I equals V times Y, or Y times V if you're being really strict with your matrices. That's V equals IR, isn't it? Because Y is equal to 1 over R. So I equals V divided by R is essentially what that means. It's just the application of Ohm's law in matrix form. So here's how you build it. If you want to do the more challenging approach, right, with a bunch of Z's, you can see that's a lot of work, isn't it? I don't want to build it with a bunch of Z terms. I'm just going to add all my Y terms and go from there. But if you want to build it from scratch, here is how you can do it. Or you can just enter it into your calculator using a bunch of 1/overs. That's usually the most efficient way to do that. Now you can solve for all the bus voltages. You actually can solve for every single bus voltage using this approach. And in some cases, if you're trying to do a really simple load flow analysis without including really any load, because you notice we didn't have any load on this system, right? All we had were a bunch of impedances interconnected. So for any system that you run no load, this system works really well. This is how you calculate it. And when you do short circuit analysis, most of the time, although that's changing a little bit, most of the time, what you would do is what's called you might do either a flat start, assume every voltage is at like a 1.03%, sorry, 103%. You'll understand where the 1.03 comes from. Or you could do this current injection approach, which calculates some voltages at buses throughout the system if you want to be a little more accurate in terms of your fault current calculations. A lot of people just do a short flat start because that's most conservative, right? If all your voltages are at 103%, then most likely your currents are going to be at their maximum when you're using that flat start approach. Where over here, you can get a little more refined. So solve for the bus voltages. V equals the inverse of Y times I. Notice the dimensions are really important here, right? Because with matrices, you got to be careful about checking dimensions. Everybody knows about the dimensions of matrix. your inner elements have to match, and then your outer rows have to correspond. So if V is an n by n matrix, then we know that our Y matrix has to be n by n. Anybody know why Y has to be an n by n matrix? Can you take the inverse of a non-square matrix? Maybe some weird mathematical trick you can do, but I've never seen it done. So your matrices are going to be square, at least in this class. Like I said, if you're taking a 400 level or beyond MAT class, they might be able to do inverse matrices and non-square matrix. But in our class, we'll just make sure that they're all square. So my I matrix also has to be that way too, right? So if I take V and I multiply it by Y inverse times I, then V, which is an n by 1 dimension matrix, is equal to an n by n, because when you invert a matrix, you always end up with the same dimensions. And this is an n by 1 matrix. So these match, right? Those inner dimensions match. And then the resulting matrix is here, which matches what we have there. So it's important, and this is where when you start using your calculator or if you start using MATLAB, you've got to make sure you're entering things in the right order. It has to be V equals the inverse of Y times I, not I times the inverse of Y, because you'll get dimension problems. All right, so if I want to multiply matrices in my calculator or in using MATLAB, I've got to make sure that my voltage matrix is equal to the inverse of my Y matrix times my I matrix. Has to be in that order. I cannot put it in my calculator, V equals I times the inverse of my Y matrix, because the dimensions will match and you'll get a dimensional error. Okay, just can't do it. Something that, the reason why I go over it again is a lot of times as seniors, you often forget, like you just forget to keep track of the dimensions, because when you use Ohm's law, it's V equals I times R. No, in this class, it's got to be V equals R times I. Okay, see, that's the huge difference. It doesn't sound like a difference, but it's a major difference when you're talking about matrices. V equals R times I.
Why R?
R? Well, the inverse of Y is essentially the impedance matrix, right? So when you invert it, you end up with a bunch of impedances. All right, so let's add some numbers to that system. So it's a 4-bus system. And we see we've got some voltages. And we see we've got some impedances, some that are in series and some that are not. And we have a 4-bus plus a reference bus system. So we label our buses, bus 1, bus 2, bus 3, bus 4, and our reference. So step 1, remember, before we do anything with admittances, is all those admittances that are in series with each other, we put them in parallel. So all these have to be added first before we can do any admittances. Once we add that, then we're going to invert every single element and start building our Y bus. So let's take a look at that. So I solve for Z1 first, which is those series combination of generator 1 internal impedance plus a transformer. I do the same thing here for 2. So this is, I'll put step 1 here, here, and here. So my Z2 is the internal impedance of generator 2 plus the transformer impedance. And Z3 is the generator internal impedance for generator 3 plus the transformer. Add those all together. And now I can invert and get Y1, Y2, Y3. I'm also going to invert and get Y12, Y23. And then Y12, get Y12, Y14, Y23, Y24, and then Y34. So that's all those individual elements. And then I've got to calculate currents, right? Because I'm doing KCL or nodal analysis. So I do a Norton equivalent on all the generators. And my current sources now are IG1, IG2, IG3. Now I stuff those in my matrix. So my self admins is going to be Y1 plus Y12 plus Y14. Sum those. Y22 is just Y2 plus Y21 or Y12, right? It's the same impedance going back and forth. Plus Y23 plus Y24, right? We have that additional bus connection. Same thing for Y33, Y3 plus Y23 plus Y34. And lastly, Y4 is Y14 plus Y24 plus Y34. Again, these negatives are because when I invert the J term, I end up with a negative J. The off diagonals are just the negative of the actual admittances between the bus. So Y bus 14 is equal to the negative of Y14. Same thing for 2, 4, 1, 2, 2, 1, 2, 3, on and on and on until you get that. And then I can build my admittance matrix there. Then I stuff in my currents. Now I'm going to go ahead and solve for my voltages. The inverse of Y times I equals my voltage. And when I run that through my calculator, that's what I end up with. Questions on how to do that? Not a hard thing to do. Doesn't take a lot of, partial derivative calculus to figure that out. But it's so important that you do it in this format because we rely on the system being laid out this way. And if you do it differently, it ain't gonna work. Yes, sir.
Actually, hard to write that in MATLAB at the inverse matrix times that in MATLAB.
How do you do it?
Yeah, you write.
So let's see. I happen to have stuff from earlier. And let me just show you. Here's a matrix, a VI matrix, we'll call it. You can see it's a 3x3 matrix in MATLAB. Doesn't have any complex numbers in it, but it could. MATLAB doesn't care. So if I want to take the inverse of it, whoops, all I need to do is raise it to the -1 power. So it's y to the -1. You can also go inverse IVN of y. And there's something called left divide in MATLAB. You could do that as well. But raising it to the -1 is the same thing. So if you see here, I take this, and that's my impedance matrix for that previous problem. Okay? So entering it in MATLAB is just like entering in your calculator.
And then we times the current.
Yep. Multiply by the current. Everybody remember how to enter the currents in the MATLAB? Using Euler's or Euler's identity. M e to the j theta. So
the angle. I believe you times again the angle because MATLAB only takes radian.
it only takes radians. So like this one right here, if I wanted to do 1.2 at an angle of 90 or -90, I think it was. The way that I would enter that in is I go 1.2 times e to the -j times 90. But then I have to convert that to radians, which means multiply by that. And we know that 1.2 at an angle of -90 is just -j 1.2, right? And that's what's confirmed here. So that's how you enter in complex numbers or polar complex numbers in MATLAB. Okay. All right, so we'll do some of that in lab. You also have a homework to practice that. So we'll go through this again in lab. We'll have problems, but I encourage you to just try to do the lab and see how it works out for you just by doing it manually, and then you can go from there. We'll talk about three-phase power systems because that is what the utility world works at. This building is fed with a three-phase transformer. I should back that up. It's 3 single-phase transformers connected, I believe, a Y on the high side and a Y on the low side. Does anybody know where the power that comes in the barrows where the transformers that step it down into, the old barrels, not new barrels. That's new barrels. That's a pad mounted transformer over between Neville and Barrows. Anybody know where the transformers are for this building?
Are
The
they
old
in the
building? In the basement, right across from my office. If you walk in, there's a special door that's like danger, high voltage. If you open up that door and you have the special key that opens up that door, you can walk in and they have they're pole mounted transformers. So they're round, they look like trash cans and they're right in the middle of the room, just kind of, and you can walk right up to them, but they have a little bit of a tape, if you will, that you're not supposed to walk up, but it's live 4160 that goes into the building. And so that used to be the most common way to get power into a building because, you know, I can run a lot of power at 4160 with very small cables. But the whole building, let's say it's all at 208, I need to run much bigger cables to distribute the same amount of power. So it's more cost effective to run as high voltage a cable as you can until you actually need to distribute the load. There's one tiny incy-bincy problem with that concept. Anybody want to guess? Usually cooling is not too bad of an issue. I said there are 3 single-phase transformers in the basement of Barrows right across from my office. No, it's locked off, right? Pretty heavy-duty metal door. Be kind of a drag if there was a fire, wouldn't it? They're filled with oil. So if there's a fire over there, it might not be a good thing to put the fire out. So you can put transformers still in buildings. Dry type transformers are not a big deal, but oil filled transformers are so much cheaper and so much more common that they usually run oil filled transformers like they did for the new Barrows, and they just run short secondaries that run into the building. So oil is a fire hazard. That's the real reason why. But back in the day, fire schmire, right? You don't see smoke alarms in this building or smoke alarm. You don't see fire suppression systems, right? Sprinkler systems in this building. Or most new buildings, I think in 3 apartment building, 3-unit apartment buildings in Bangor, you have to have sprinkler systems. Look at this building. This building doesn't have any sprinkler systems in it, so it is what it is. But the reason why we get into that is almost everything you'll see with any real power demand is going to be 3-phase, and it's a balanced 3-phase, which means all the voltages have the same magnitude or about the same magnitude, and their phase shifted by 120 degrees. And most real world power systems work really hard to maintain that magnitude, voltage, and balance. That means you also have to have equal loads on the system, which that's not as guaranteed, right? Because if you've got a bunch of customers that are down one street and you run what's called a radial line off to those customers, if they're pulling a lot of power for one reason or another, and your next neighborhood down, who's off of a different phase, is hardly pulling any power, you're going to have an unbalance. But for you as an individual owner, try to balance out the loads as much as possible, which means buy as many 3-phase loads as you can. Buy 3-phase motors. They're cheaper and they're more reliable. So get as many 3-phase as you can. The other thing is that the impedances on the line are all about the same, which usually is not too bad, because if you run the same type of cable between point A and point B, the wires are about the same length. So that's usually a pretty easy thing to do. And so almost exclusively, almost the entire power system in the entire world, not just in the US or North America, in the world is run with 3-phase. Exceptions, DC systems, right? We already talked about the high voltage DC systems that now come into Maine, and there's also one in Mass. There is a 6-phase system in Africa. I think it's in South Africa, but it's very limited application. There was a trial one set up in New York to do some research, but it never really went anywhere. So almost every system you'll ever come across, even if it's a medium power system, is going to be 3-phase. Like coming into campus, at the top and bottom of campus, those are both 3-phase interconnections. So here is a balanced 3-phase system. And if it's a balanced 3-phase system, all these currents are going to go to the load, but the currents all have the same magnitude, but are offset by 120 degrees. We love to do vectors, right? So one current looks like this. The other current, we're going to add it to this. and the other current is going to add, and if I could draw, gets back to that point. So the currents going into this neutral circuit, when you sum them together, are equal to 0. In a perfectly balanced system, a neutral has no current, which means the neutral is 0 volts. And most neutral systems are connected to ground. And because there's no current in there, most of the time in a balanced system, why would I run that conductor? It costs me money. So most three-phase systems, you don't even run a neutral to it because it's not being used for anything. There isn't even a place to connect it. So almost all your balance, your three-phase systems, you don't run the neutral. You still have to run a ground conductor, but you don't have to run a neutral conductor. So the utility system that you see a three-phase system, like when you see overhead transmission lines, those are 3 hot phases, A, B, and C. And then usually overhead, not always, but usually overhead, you'll see a small bare conductor. That's your ground wire. That actually is not the ground that you think of. That's not the ground that interconnects the two systems. It's a ground that actually provides some lightning protection. So if the pole gets hit, it goes to that ground wire, and then it can go and can conduct to ground. But it actually isn't necessary to run for return path because we're standing on ground, right? Isn't that perfectly fine? And the other advantage is if it's a balanced system, no current goes to ground. They just travel back through their other phases. So in a neutral system, in a balanced system, you have no neutral current. And the other advantage is in a perfectly balanced system, I can look at any one phase and do calculations on those one phases for power. And you can see that here. If all the systems are balanced, my voltage and current for phase A have the exact same magnitude for B and have the exact same magnitude for C. Also, phase A is phase shifted by whatever the phase shift between the two is. But phase B is also phase shifted by that exact same amount as is phase C. So any one of these 3, I can use to calculate what my total power is. And that's what we do. And you'll see this last equation over there, S equals 3 times VAN times IAN conjugate. You just as readily could have said it was 3BN times IBN, or 3 VCN times ICN, the conjugate of that. Any one of those will give you the exact same result. So we've talked about it a couple of times, and we even see it when we were looking at our bus example. We oftentimes work off what's called a single line diagram because one of the phases matches the other two. They're all the same except for the phase shift. So why bother drawing 3 phases if you're going to get the same results? So using single phase analysis. But this only works if this neutral is at 0 volts. If the neutral is not at 0 volts because you have an unbalanced system, then those voltages, VA, VB, and VC, are not balanced. And we'll see at the end of the semester how to do analysis with unbalanced systems. So you can only do 3-phase balanced systems calculation we're going to be doing for the brunt of the semester if you have a balanced system. Okay. So what is the advantage of 3-phase power? Can transmit way more power. In fact, twice as much as a single phase system. And you can say, how can that be? Well, if I have no idea why that keeps them. Here's my 3-phase system. And I only run 3 wires out of there, right? If I have 3 single phase systems, how many wires do I have? Are the same, but we'll learn about the difference here. Those voltages are not the same. They're actually higher. But it can produce that. This is a huge advantage of the second bullet. Torque produced by a 3-phase machine is constant. And any mechanical engineering folks in here? Anybody here have a hybrid car? No? One of the worst things you can do is have vibrations for mechanical systems. And it just causes damage. And so the lesser the vibrations, the smoother it's running. Usually that means it's going to last longer. And so if you have a machine that is vibrating, most of the time it's got problems with one of the windings. It's not putting out a constant torque. What I mean by that is there's something called the rotating magnetic field. If that rotating magnetic field is not constant, then you're going to get some vibrations and your machines aren't going to last nearly as long. Three-phase machines use way less material for the same power rating. So remember how I said three-phase machines are cheaper? There's the reason why, less copper. You need less copper to make it work. And starting a single-phase, three-phase machine is, if you can, is flipping the switch. You energize that three-phase machine as long as your system can handle it, meaning the voltages don't drop too much, the machine will start and get up to speed very quickly. Where single-phase machines, you have to have capacitors in there to make it work. And oftentimes you have what's called a start and a run capacitor. So more complexity, more stuff, they don't last nearly as long. So three-phase machines are cheaper and more reliable. How often does that happen? You have a more simplistic machine, less parts, less material, cheaper, but it actually can put out more power. And it's all because of the available voltage. By the way, I would be willing to bet that none of you in this classroom have three-phase power at your residence. Anybody here does? If your folks or you know somebody who has like a really fancy-dancy wood shop at their house, maybe they would do it, but they're paying a heck of a lot of money for that three-phase connection because you need, the utility won't even run you three-phase unless you can prove you've got enough demand or enough load. If you don't have enough demand or load, sorry, you're going to be running 240 volt. That's what we're going to give you. You have to prove that you're going to get three-phase. Like a Walmart, you know, that's a no-brainer, right? They're going to have 5 MVA of load, no big deal. They'll run it because the utility, again, is going to get paid. But if they could supply you with 240, it's cheaper for them. They're going to feed you with 240. Yes, sir.
So, a lot of four things.
Knobs, your burner, yeah.
Might be, but,
That's what that would be actually, that's called single phase.
oh,
So remember way at the beginning, I think it was the beginning of this class, the transformer that goes to your house looks like this. So let's say it's 7,200 over here and across here to here, it's 240 volt. That's what goes to your stove. The reason why you can plug in is because it's called a center tap and each one of these is 120. So it runs to your house, the single phase 240, but then you center tap the transformer and then you can get 120 off there as well. Now, for those of our friends in this class that are from overseas, Europe, they run 220. They don't have 120. So that's why when you plug in your cell phone and it burns up, it's because the voltage that you plug into the wall over there is all 240 volt, or I'm sorry, 220 volt. That's why if you talk to some old school electricians, maybe even some of the folks at the MCC, they call it 110, 220, right? Have you ever heard that? It's 110 circuit. It's a 110 circuit. Hasn't been 110 in North America, where they would actually say 220 and then somehow it got transferred to 110. I guess 220 and 110 sounds nicer to say than 240 and instead of 120. I don't know. But see, people still call it, like my dad says 110 still. And I'm like, no, it's never been 110. So not in your entire life. So how do you connect? Three-phase machine. We got two choices I will talk about in this class. There are more than two, but these are the vast majority of the ones that you'll come across. You have a Y or a delta. Why? Because it looks like the letter Y. If you squint and you flip it around, that right there looks like a Y. The other one is delta. It's the Greek letter delta. So we'll look at that in a minute. But the way you connect them is you have a neutral and all your individual power supplies are connected minus a plus away from the neutral. That's just the connection diagram. But each of those individual power supplies all independently have to be internally configured so that they have the same magnitude and phase shift. That's why when you were talking about, a generator, the windings are physically configured on the machine. They're physically located on the machine so that you get an electrical 120-degree phase shift. And so the reason why I'm telling you that is because I've had previous students in the past. We want to build a three-phase power system. We want to grab the function generators that are in the lab downstairs and connect them with their negatives and build a three-phase power machine. It's like, no, that doesn't work that way because you don't introduce the phase shift. So if you actually want to go ahead and do that, you actually have to build something that can build in 120-degree phase shift, which means you need power electronics. So for those senior project folks who haven't picked theirs yet, that's a really cool one. Most of the ECE folks don't even, if you did a three-phase power system or power source, I suspect you'd get a straight A because everybody in ECE would be like, what? How does that work? What are you talking about? Because that's not something that they do. It's not a put down on them. It's not that common. And all it is just taking a bunch of essentially semiconductor devices and switching them on and off in a pattern so that you get three-phase separation. We had a student group who demonstrated that last year, right, B?
Yep.
No one right here. So it's not easy because you got to time things, but it's not that difficult. And like I said, if you're located kind of near, if you're located in town, but you are, let's say you're down at the bottom of a hill and the water treatment facility is on the other side of a hill, what you got to do is you got to pump your nasty stuff that's on the other side of the hill because stuff goes downhill. It goes to a holding tank at the bottom of the hill, and all that stuff has to be pumped over to the other station. And so a lot of times, like those pumps are located not in the most populated area, so the utilities don't even run three-phase there. But you can take two-phase, you can run it through what's called a variable frequency drive. It converts the AC incoming to DC, and then you just cut that DC up into three-phase, which is exactly what you did, and you get a three-phase power source. So if you want to build a three-phase power source, you can actually go buy one from Automation Direct and buy a VFD, and it'll take three-phase, single phase in and give you three-phase out.
They only need two phase and bring out a three phase. Why have to use one phase, but then you use two phase?
You can use one phase, yeah. You could use one phase, yep.
But one phase, does using two phase give more power or?
If you get it set up right, it gives more power because you can set the DC up for higher. But if your single phase system is strong enough, when I mean two phase, you get two wires running down, and then you run across those two phases, so your voltage is just higher. That's all it is. But that is a Y connected circuit. How do my voltage compare? Well, this is where we got to get into a little bit more discussion. We have a phase voltage. This is a phase, and the voltage across those two lines is called the line voltage. Okay. So a phase voltage and a line voltage exists in three-phase systems, and phase currents and line currents also exist. So if I look over here, this is the phase current, which also matches the line current, right? Because KCL, the current in equals the current out. Over here, I have to vectorially add VAN and VBN. So if I wanted to go VAB and get the voltage potential there, I would just do a KVL loop around it. And what I end up with is this equation over here. So when I do my KVL, my line voltage, which is VA to B, is equal to the square root of 3 times the magnitude of the phase voltage, and then the angle of the phase voltage plus 30 degrees. All right. VB is exactly the same, square root of 3. But again, I still have to maintain 120-degree phase separation. So now I have to do minus 90 from that initial phase angle. And the same thing for 150. So why do we like three-phase systems? Because our line voltages and our phase voltage all have the exact same magnitude. Well, not the same magnitude, the same magnitude amongst themselves. So all the line voltages in a three-phase system are the same. All the phase voltages are the same. When you start talking about four-phase systems, hopefully you can see that the voltage from there to there is very different than the magnitude of the voltage there if I just add the magnitudes together. So, because you think, hey, let's keep going 4, 5, 6 phases. Now you just made the electrician's job a lot more difficult because now they really got to keep track of how they run the wires. In most industrial facilities, you know how they run the wire? They just pull it and connect it, see what happens. Sometimes they keep track of phasing. More often than not, they just pull the wire and don't even worry about it because the load doesn't care. If the load is rotating in the wrong direction, you just swap a couple leads and it rotates in the correct direction. Very, very simple and basic. So phase voltages are balanced, line voltages are balanced in a Y connected system. Yes.
The way you can measure the angle of voltage, but let's say you have three-phase wire. The way the machine which can measure, find what's the angle between them, which one is a zero, which one is a one thing.
There is a device called an oscilloscope, right? You can use an oscilloscope to actually look at the waveforms. You can have a phasor analyzer that is going to be able to do it, but you have to pick a reference phasor. So one has to be your zero angle, and then the other ones have to be based off that. But the easiest way to do it is use an oscilloscope. It's the easiest. Do you have a question?
Does V-phase typically say negative 120 phases, or is it typically negative 120 or 120? Like, I didn't know.
Well,
Which season.
so you can do either one. So there's something called positive sequence rotation and negative sequence rotation. Positive sequence will usually be A at 0, B at minus 120, and C at positive 120. But if you go negative sequence rotation, A at 0, C at minus 120, and B at positive 120. So there are cases when you switch those around. And when we talk about what's called symmetrical components, you'll actually see where we'll have to switch that around. So if you want to use Euler's identity, right? E to the J pi over 6 using radian modes, not degrees. And we have our line equals phase current. Line does not equal phase voltage, but S equals 3 V phase, I phase conjugate. That always holds true. In a delta, the phase and line voltages are the same because that's the phase and that's the line. It's across two voltages or two lines. So there is no difference between line and phase. The currents are different though, because the current that I can see here is going to be the vector addition of ICA and IAB, right? And so when I do that, I end up with that square root of 3 term again, times IAB, and the angle is minus 30 degrees. You can do the same thing for B and the same thing for C and get the same results. Power is still the exact same thing, 3 V phase times the conjugate of I phase. And then if we did the phasor diagram for currents there, I didn't talk about that for voltages, but essentially you can just see how you've got currents, the phase currents are different than the line currents. We don't bother showing the phase voltages and the line voltages on a delta because they're exactly the same. There's no difference. There's no phase shift. There's no magnitude difference. They're the same. So let's take a look at an example. If for some reason you needed to do a full 3-phase analysis, you have a delta connected load is supplied from a 3-phase 13.8 kV. That's a line voltage. So one of the things we have to be aware of is what is the typical voltage in this class that I'll tell you. I'll almost always give you the line voltage. And that's because if I tell you the line voltage, that's usually going to be the highest voltage. So if I'm going to go work in a substation, I want to know what the highest voltage I'm going to be prospectively seeing because I don't want to get zapped. I don't want to buy equipment that's rated for 50 kV when I could be seeing 85 kV. So when you walk into Orrington, you see it's 345 kV. That's 345 kV nominal line voltage. The actual voltage is a little bit higher. It's like 352, 353. But the nominal line voltage is 345 kV. The phase voltage would be lower if it's in a configuration like that. So here's a Y-connected source, right? Not even Y-connected. It shows a neutral there, but it doesn't have to be one there. It could be delta. But I have a delta-connected load is supplied from a 3-phase 13.8 kV source And the load is 100 at an angle of 20. So I want to go ahead and calculate some currents here. I'm going to calculate line currents and phase currents. And so first thing I got to do is define the voltages. So I'm going to just pick my line voltage for VAB, the voltage across lines A and B. That's the 13.8 nominal kV voltage. And I'm going to pick that as a reference of 0. My BC is going to be 120 behind, and my CA is going to be 120 in front of. Technically, it's not in front of, it's actually minus 240, but we just call it, we make it easy with the math there. So to solve for the phase current, this is I phase, right? Which is the current right here flowing through one of the phases in the delta. That's the voltage across it, which is our phase voltage or line voltage, divided by the impedance, 100 at an angle of 20. And when I do that, I get 138 at an angle of minus 20 amps. I can certainly plug in 13.8 kV at an angle of minus 120 and divide that by 100 at an angle of 20. But I don't need to, because I know that the currents are phase shifted by 120 degrees. So I can just plug in a phase shift associated with it and end up with 138 at an angle of minus 140, or 138 at an angle of 100. By the way, should I be adding plus or minus 120 to the impedance there? I added 120 to the currents and the voltages. Do I have to add that to the impedance?
No.
Absolutely not, because voltages and currents are phasors. Impedances are fixed device. So it's always going to be 100 at an angle of 20. It never changes. But the currents, I do have three-phase voltages and currents because those are phasors. I do not have, there's no such thing, and I'm going to say this about 50 times a semester. There's no such thing as a three-phase resistor. There's no such thing as a three-phase inductor. There's no such thing as a three-phase capacitor. There is a three-phase, be very careful of the wording here. There's a three-phase load, resistive load, that consists of three resistors that are connected in delta or Y. I said three resistors, not one. So I don't want to ever see an answer that says I've got a 300 ohm three-phase resistor. No, I have three 300 ohm resistors connected in Y or delta to make a resistive load. Yes. Yep. Now, even the motor, right? Let's say I have a three-phase motor load. That's 100 horsepower. The motor looks like 100 horsepower, but there are three phases inside the motor, separately individual phases that are interconnected at one point, and each phase is responsible for 1/3 of the rating. So each of those phases is doing 33.3 horsepower worth of work. Okay. So with all this stuff, we talk about three-phase. There's no such thing as a three-phase, truly a three-phase load. There's a three-phase source, but even when we look at it a little bit zoomed in, those are three single-phase sources just interconnected and set up at 120 degrees to get what we need. So here are our currents. Now I can go ahead and actually calculate the line current. And the reason why I want to know the line current is I've got to put a breaker in here and here and here that will protect the line from excessive load. So if I set that at 138 plus some margin, it may trip, whoops, because the actual current going through that line is 239 amps, or square root of 3 times. So line currents are pretty important to know because that's the actual current going between devices. And if I want to calculate the total power, I do 3VI conjugate, that's phase quantities. You notice it's 138 amps, not 239 amps. And I end up with 5.7 at an angle of 20, or 5.7 at a 0.94 lagging power factor. Yes, sir.
Find the line current between the phase current minus other phase current.
Well, there's two ways to do it, right? The one way that I can do it is if I just do KCL over here, I can solve for IA, right? the current in equals the current out. So if I know these two currents here and here, I should be able to solve for that current using Kirchhoff's current law. Right? I also can take 138 and multiply that by the square root of 3, and I'll at least get the magnitude. Not the angle. The angle I either have to add or subtract 30 degrees. It depends if it's positive sequence or negative sequence. Because if I look over here, it's 138 at an angle of minus 20. If I look over here, it's 239 at an angle of minus 50. So you can see I had to subtract 30 degrees. But anybody verify 239 divided by square root of 3? What do you get? I can do it in MATLAB here too. 239 divided by the square root of 3. What do you think it's going to be? What do you know? 138, right? So you did it, or we did it here in class with KCL, and we just proved that that 138 is where that comes from. Okay. And then the power, the S is just 3 VI conjugate. Yes, sir.
You know, the way you solve it is the only way to solve it because you don't know if it's, which sequence is it.
Well, no, we actually do, because if we look over here, we define the sequence to be ABC sequence because we went VA was first, and then VB was next, and then VC. So we did that here. So we assumed positive sequence by assigning those angles.
So A, B, E, A, what's the negative sequence?
Negative sequence would be these two would swap. It'd be plus and then minus. Okay. So if you ever have mixed systems where you have a delta source or a Y load or vice versa, it's usually much, much easier to make them all the same, and usually much easier to convert them all to Y. So if you have a balanced system, if you remember back from your circuits where you had a three-phase system and they had said Z1 is equal to this combination, divide by 3, whatever. Over here, because they're all the same, it's really simple. ZY is equal to Z delta divided by 3. Much, much easier. You don't have to keep track of the equations. And then if you have a delta connected source, you can convert it to a Y just temporarily, right, to do the analysis. And you divide by the square root of 3. And that at an angle of 30 degrees is only if it's ABC or positive sequence rotation. Usually, if you assume positive sequence, you're going to be okay. There are a few systems that are negative sequence. I'm not going to bother showing you the proof. This is something you saw back perhaps when you did your intro to circuits classes, but you can check and see what the proof is because we're running out of time. And here are some three-phase transmission lines. This is, I believe that this is if you're on Dirigo Drive in Brewer, which is if you're on Wilson Street. Everybody know where Wilson Street and Brewer is? So behind, or that used to runs parallel for a small amount from Eastern Ave, I think, not Eastern Ave. It's the one that has Brewer High School on. If you run that, there's an emergency vet, and you kind of run up there. Before you get to the top of the hill where the cancer center is, you actually are going to go under those three-phase transmission lines. And I believe that's the picture that you see. So those are the three-phase lines going into Orrington. And just shows you pretty simple construction. In Maine, we go with H-frame construction. It's cheap. Plus, we can go pretty straight. You can look, it's hard to tell, but these lines are almost exactly perfectly lined up with each other. That way you don't need to worry about guy wires. It's once you start doing twists and turns is when you got to start getting more creative with guying. Because if you think about it, all these wood poles do is keep the wire up in the air. Because a wire is pulling this way, but that same wire is pulling this way. So they balance each other out. So there's no force at the top of the pole other than keeping it from falling on the ground. So most telephone poles, that's the reason why they can just dig a hole that's 5 feet, 6 feet deep, drop it in the ground, and then they can walk away from it because there's not going to be any pulling in either direction. All the attachments are run in, you know, they're kind of run, they're parallel to it, not parallel, but they're tangential to each other. They're pulling in opposite directions. It's when something comes in this way and goes out this way, Now I've got to have an opposing force in this direction and one in this direction. That's why you're gonna have guy wires. So when you go down south or in more urban areas where you can't get straight lines because the land is too expensive, you got to start running all different directions. They use a lot of steel poles because with a steel pole, you have to design a foundation, and that steel structure is designed to handle all the forces at the top. So steel poles don't use guy wires. They just use a bolted concrete foundation. And if you want an example, a good example, probably an overkill example, is if you go in Bangor on Stillwater Avenue, there's a Chili's in Bangor, if you're familiar with it. If you go towards the front of the parking lot, you see this massive concrete like structure. There's three of them where they have this 46 kV line from Bangor Hydro that goes over by the mall, and they have a hard angle, and that's where they put it in. Yes, sir. Yeah, so that's different. So you're talking about in Brewer, right? Yeah, just outside of Brewer. So if you're going towards Ellsworth, the 395, you see some massive steel poles there, but those are tangent poles, I believe. Anybody know why they use steel poles there? Because now you're talking about a really long span. It's hard to get a tree that's going to be 100 feet tall that's perfectly straight. So when you got to get really tall and you're running very long distances, you got to run steel poles because the sag of the line will be so great that you just got to increase the height. So it would be better to do it with wood poles if it's practical, but the spans, because you got to get all over that roadway, you got really long spans there. It's not practical. All right, any questions? People are bailing out. It's not even, class is not even officially over with, right? It's 1:45?
Oh, yeah.
Not 1:45, just turned 1:45 and people are already walking out the door. I guess they're ready for the weekend. All right, party people, anybody on TV land? You're all present. Nothing? Okay,
Hey, Paul?
well, you all have a great day. Riley, are you trying to say something? I can't hear you.
Yeah.
You have a question?
Can you hear me now?
Yeah, go ahead.
Oh. This summer I did some work and there was a PV field up in Maine and they lost their grounding transformer.
Yep,
And I didn't get like a full answer on what it was, but a zigzag transformer.
yep. It's a special type of transformer to provide a high impedance ground. Yep.
So I looked up, I did some research and I had some explanation given, and they're good for like the third harmonics. Are we going to do anything in relation to grounding?
We talk about it, but we don't do zigzag transformers because it's more of a special topic. So you don't come across those all that commonly.
Yeah.
So I can explain them to you, but for the most part, most people in this class will never come across them. So we don't spend a lot of time with zigzags.
Okay.
Okay.
Sounds good.
All right.
Have a good
All right,
weekend.
thanks, Joe. Have a great weekend. Bye.